Welcome back to my YouTube channel all about VLSI. In this series of Ethernet MAC controller design, this session we are going to discuss about TX FIFO. Now, in this particular TX FIFO, what we are going to discuss? Let's try to understand. Now, this particular TX FIFO, why we are going to use? See, we have the processor which is present with us, and this particular processor is trying to communicate with our MAC controller using AXI interface. So, using the AXI interface, it is communicating with our MAC controller. This controller is also wrapped in AXI interface, right? Now, inside this controller, we are going to have the main module. Now, this main module is going to control your SFD module, preamble module, all the other modules we have discussed right previously. Those all modules will be controlled by this particular module, which is known as TX MAC control. Now, this particular TX MAC controller is working with a clock, which we are getting it from the receiver side, which is nothing but my TX clock. You can see over here, the processor is working with external clock and providing the data via this AXI interface. And the controller is basically working with different clock, which is nothing but my TX clock. Now, both the clocks are different. Here, let's say this is external clock. Okay, so both the clocks are different. They are having different frequencies. And in the previous session, when we are discussing about asynchronous FIFO, we have seen that in this particular case, we are going to use an asynchronous FIFO. Now, what is it we are going to do in the asynchronous FIFO? So this is my processor and this is my MAC controller. Okay, so this MAC controller is now working with different clock, which it is getting it from the physical receiver. Okay, TX clock, we have seen right how we are going to get the TX clock and all. Now, here we are going to use an asynchronous FIFO. So my my processor is going to feed the data into this asynchronous FIFO, and MAC controller is going to retrieve the data from this particular asynchronous FIFO. And here the processor will come into write clock domain, and my MAC controller will come into read clock domain. This is very, very important over here. So my processor is writing the data into this asynchronous FIFO. That's the reason it is coming into write clock domain. And my controller is basically reading the data. So that's the reason it is coming under the category read clock domain. So the processor, since it is coming in under write clock domain, it is going to have access to the signals, which is full and empty. Sorry, only full, right? And if the processor wants to write the data into this asynchronous FIFO, it is going to give the signal write enable. That means processor is having the access to the pointer write pointer, because this write pointer is implemented in the write clock domain, and this MAC controller should pass the read pointer value, not exactly the MAC controller, the read side should pass the read pointer value, so that this particular FIFO can calculate full condition, okay, by using this write pointer and read pointer. And same like this MAC controller is going to have the access to empty signal, and it is going to provide the read enable signal. Now, the read side is going to have access to read pointer. And if this read side clock domain wants to communicate, wants to generate empty signal, it should have access to write pointer, which is present in the write clock domain. So this write clock domain is going to pass this write pointer to the read side so that it can calculate empty condition. So this is what we are going to do. Okay. Now, so we have declared a model TX underscore FIFO, and data width we have declared, FIFO depth we have declared, and address width is basically find out using this log operation of FIFO depth. And we have something known as almost full threshold, which we are taking it as 8. So it will be flagging when less than or equal to n slots are going to remain. Okay. For example, if my FIFO depth is 16, and if I have written all the particular locations, like if I've written 8 number of locations, so 16 minus 8 is nothing but 8. So I can say that my almost full threshold is equal to 8. Let's just suppose if my if I'm going to write only 7 locations, then it is nothing but 9. So this particular flag will not be given. And similarly, almost underscore empty underscore threshold. Let's say suppose if my FIFO depth is 16, and if I read from 12 locations, then it is the difference is 4. So that means this particular flag will be given almost underscore empty. Let's say suppose if I read from only 14 locations, then what is this 16 minus 4, which is nothing but 2. Okay, so that means you are going to this particular empty signal will be made to 1. Let's say suppose if this is 16 minus 10, which is equal to 6. Okay, then that means this particular flag will not be made to 1. Okay, so this is how it is going to work. And this is my right side signals. That means the processor is going to have access to this particular signals. What is this W clock, which is right clock domain, this one. So this one clock, the processor is going to provide this clock and actively reset and write data. This is what the processor is going to write into the FIFO and end of frame underscore n. Now, what do I mean by this end of frame underscore n? Let's say suppose if this is my FIFO and I have few locations like this. Let's say 1, 2, 3, and 4 and 5 locations. Now, my frame can be 2048 bytes, right? Now, if my frame is 2048 bytes, and if the processor is writing all this particular bytes into this particular FIFO, now, how my receiver is going to know what is the last byte, how it is coming to know. So using this particular end of frame, it is going to come to know that, okay, this is the last frame the receiver is going to come. So using this signal, the receiver is coming to know that this is what is the last frame which is present in this particular FIFO. Using the signal, we are going to come to know. And for that, what we are going to do is, if this is my byte of data which is present, which is of 8 bits, to the last frame, to the last byte, what is processor is going to do is it is going to take one more extra bit and it is going to make the MSB to 1. So whatever the remaining bytes which were before this particular last byte, the MSB will be equal to 0. So in this particular process, what we are going to do is our actual data width is 8 bits. That is, processor is going to send byte by byte into this particular FIFO. 1 byte information it is going to send. Now, we are going to add one more extra bit to this actual data, which is going to indicate the actual end of the frame. Let's say suppose if the MSB is equal to 0, which is showing the status. That's it. Okay, if it is equal to 0, that means it's not the last byte information. So the receiver will come to know, okay, this is not the last byte. So that means still there is data which is pending. And let's say if my MSB is equal to 1, okay, then that is the last byte. Now, this is about my end of frame. And I have something known as SAF underscore mode. Now, what do I mean by this SAF underscore mode? SAF basically stands for store and forward. Now, what do I mean by store and forward? Let's try to understand. Let's say this is my processor and this is my FIFO which is present and this is the controller. Now, in the case SAF is equal to 1, which is nothing but store and forward mode is activated. In this particular case, until and unless processor has written into all the locations, until and unless the processor has written into all the locations, the controller will wait. It is not going to read the data from this FIFO. If the processor has written all the data information, if it has sent all the bytes of data, then only controller is going to read that particular information. How we are going to achieve this? We are going to achieve this functionality using the empty signal. So unless and until this is my processor and this is my FIFO and this is my controller. So in the case of my SAF mode, if the processor has written into all these particular locations, then only controller is going to read. Let's say suppose end of the frame is not yet occurred in this particular FIFO, then the controller is not going to read it. Okay, if end of the frame is given only, then only the controller is going to read. That means if all the information has been written into this particular FIFO, then only my controller is going to read. Now, how are we going to achieve this? We are going to achieve this using the empty signal. So if my empty will be made to 1 initially, and this will be made to 0, then only controller can read the information from this FIFO. This we already know. If empty is equal to 0 only, then only FIFO, then only controller is going to read the information. Now, until and unless the processor is written, until and unless the processor has written all the bytes into this FIFO, empty will be 1 only. Now, generally, if we are working with FIFO, if at least one location has been filled, we will make or we will assert our empty to 0, right? But over here, in the case of my SAF mode, I'm going to maintain my empty signal to be made to 1 itself. So all the particular bytes have been written, then only I'm going to make my empty is equal to 0. Then controller is going to read. That is nothing but my SAF mode, which is nothing but store and forward. Now, if SAF is equal to 0, we are not going to normally read. That means if one location has been filled, we are going to read from that particular location. If at least one location also is being filled, empty will be made to 0. That is nothing but my cut through mode. That means SAF is equal to 0. And coming to another signal, which is frame underscore abort. So what do I mean by this? So let's say if there is any particular error in the EXA transaction, and if that particular frame is not valid frame, then I'm going to use this particular signal, which is nothing but frame underscore abort. Now, output of this particular write clock domain, as we have discussed previously, it is full, almost full, and write underscore fill underscore level. That means current occupancy level. So how we are going to know this write underscore fill underscore level? This will be nothing but write pointer value minus read pointer value. Okay. For example, if write pointer is at 5th location and read pointer is at 0th location, then the current occupancy level is 5. Okay. So this is nothing but my write fill level. Now, coming to read clock domain. So that means to this MAC controller, what are the signals which we are going to have? So we have R clock, which is given by my MAC controller, and reset in, which is also given by MAC controller, and read underscore enable. Now, this is given by my MAC controller, okay, because it is reading, right? And how it is going to get the data from the FIFO using this RD underscore data. And to the MAC controller, I'm going to have EOF underscore out, empty, almost empty. Okay. And I have some two more signals, which is ECC underscore CORR and ECC underscore ERR. ECC underscore CORR is nothing but single bit correction and double bit correction. ECC is nothing but error correction code. This is for single bit and this is for double bit. And about this error correction, we will discuss in great detail in the upcoming sessions. Now let's see about our other internal declarations. So we have declared RAM width, which is data width plus 1. So why it is data width plus 1? Because our data width is basically 8 number of bits, and we are going to allocate one more extra bit for my sign bit, which is indicating the end of the frame. Now I've declared my memory, internal memory, which is 0 to FIFO depth minus 1 and RAM width minus 1 down to 0. Okay. Now, over here, we have declared few variables over here, write pointer in binary format, write pointer in gray format, and write pointer underscore commit. Now, what do I mean by this write pointer binary, which is present in binary format, gray format? And why are we using gray format, write pointer in gray format? Also, we have discussed in our previous session when we were discussing about asynchronous FIFO. And write pointer commit. What do I mean by this write pointer commit? See, here we have seen that the processor, after completing writing all the locations, then only this empty signal will be made from 1 to 0 and controller is going to read it in the case of my SAF mode. And how to make this empty signal 1 to 0, it is going to dependent upon the write pointer, right? And this write pointer commit value only we are going to use for deasserting the empty signal. Anyways, we are going to see it like how exactly we are going to use it, right? And we are incrementing our write pointer binary next is equal to write pointer binary plus 1. We are going to increment it, right? Now let's try to understand how are we going to advance the write pointer. Now remember, write pointer incrementing is happening with respect to processor clock, which is nothing but W clock. Okay, so you can see over here, if I'm going to apply the active low reset, then write pointer binary, and when we are discussing about asynchronous FIFO, we have discussed in great detail like why are we using gray pointers when we are dealing with asynchronous FIFO. We have discussed it. If you haven't watched it at that particular session, I recommend you to once go through that. Now, this particular write pointer is incremented with respect to write clock, which is nothing but the clock which is given by the processor. Now we are basically initializing this write pointer binary is equal to 0, write pointer gray is equal to 0, and we have some variable which is known as write pointer commit. Now what do I mean by this write pointer commit? Let's see this. So when we were discussing about SAF mode, which is nothing but store and forward mode, we have seen that empty will be made from 1 to 0 only if all the particular locations have been filled, right? Now, how the read domain is coming to know how the read domain is come to know whether all the locations are filled or not. So we are for that we are going to use a signal which is known as write pointer commit. So using this signal we are going to basically assert this particular empty signal from 1 to 0. So using this particular signal which is nothing but write pointer commit, I'm going to make it. Okay, let's see that. And else if reset is not applied, then what we are going to do, we are checking for frame abort. If frame abort is made to 1, then we are write pointer binary is nothing but write pointer commit value. We are going to assign this particular thing. Okay, next, and write pointer commit will be equal to, we are going to perform XOR operation, write pointer commit XOR with write pointer underscore commit write shift by 1. So here we are going to write down write pointer underscore commit underscore gray. So here where if my frame abort is equal to 1, then whatever the value which was present in this particular write pointer commit, that we are storing in my write pointer binary. Now this binary pointer should be converted into gray format. Now how are we converting? We already know if we want to convert a binary number 0101 into gray, it's simple, 0, and we are going to perform XOR between this. We are going to get 1 XOR 1 XOR 1. This is how we are going to convert. Now instead of doing this particular thing, what can we do is 0101 we can take, and first of all we can perform right shifting. Okay, how to perform right shifting? It is 0 0 1 0 and perform XOR operation between these two, which is nothing but 0 1 1 1. So that is what we have written over here. Write pointer gray, which is equal to write pointer underscore commit XOR with write pointer commit write shift by 1. That's it. Okay. Now we have converted our binary format write pointer into gray format. Okay. Now this is when my frame abort is equal to 1. This is when my frame abort is equal to 1. Now let's say if my frame abort is equal to 0, then what are we going to do? Now, if my frame abort is equal to 0, I'm going to check for my write enable. That means if the processor is trying to write the information into this particular write enable, and I'm also going to check whether the FIFO is not full or not, whether the memory is not full or not. Yes, if it is not full and write enable is equal to 1, then I'm going to write down the data. This is my actual data and end of the frame information. I have said you right, write data is basically 8 bits and this is 1 bit. Okay, so total 9 bits I'm going to write down in my memory, which is mem underscore write pointer binary. That particular location I'm going to provide. Okay, and I'm going to store it into my memory, and I'm incrementing my write, and also I'm going to increment my write pointer binary next. So you can see write pointer binary is equal to write pointer binary next. And here my write pointer will be incremented and it is being converted into gray format. So write pointer is now converted into gray format. Now, what is it we are going to do if end of frame underscore in is equal to 1? If this is given, then we are checking for my store and forward mode. If it is equal to 1, then this write pointer commit will be equal to write pointer binary next value. So this value will be updated to my write pointer commit. Whatever the current value of my write pointer is there, right? That will be given to this write pointer commit. For example, this write pointer commit will be 0 only. This write pointer commit will be initially 0 only, right? And my write pointer will be incrementing whenever write enable was equal to 1 and full was equal to 0. It will be incrementing, and let's say it has reached the end of the frame. Now right pointer value is this, and I'm not directly giving this right pointer value to my read clock domain for calculating my empty condition if I am in SAF mode, because I should not make this empty from 1 to 0 until and unless I have reached the last particular location. So what is that I'm going to do? I'm going to use another pointer, which is nothing but right pointer commit. So this particular pointer will be 0 only, and this is given to this read logic. Okay, now that's the reason empty will be equal to 1 only. Read pointer will be initially equal to 1, and write pointer will be initially equal to 0, and read pointer will be initially 0, right? So empty will be 1 itself. Now after reaching this last frame, see what we are doing. Right pointer commit is given to right pointer binder next. What happens, let's say if it is in 8th location, then right pointer commit value will now become 8, and read pointer was equal to 0, right? So read pointer will be equal to 0 only, and right pointer will be updated. Right pointer commit will be updated to 8th location when I'm reaching this end of the frame. Now what happens? Empty will now become 0, and then the Mac controller will issue the read enable logic, read enable, and it is going to increment this read pointer. This is how we are basically controlling this empty condition, right? But if we are in cut through mode, then what are we going to do? Then we are going to give right pointer commit is equal to directly right pointer next. We are not checking for this end of the frame. Okay, so if end of the frame, if we are working with SAF mode, then we are giving the right pointer commit to this particular value if end of the frame is given. But if we are working in normal cut through mode, we are basically checking for this SAF underscore mode. If it is equal to 0, then we are going to give this particular value. That's it. Okay. Now next is my 2D flip-flop synchronizers. So why I'm using my 2D flip-flop synchronizers, we have discussed in great detail in asynchronous FIFO session, right? Now, this particular 2D flip-flop synchronizer is used to convert gray right pointer, and it is basically used to send right pointer from right clock domain to read clock domain. So the right pointer was there in the right clock domain, and it is converted into gray format, and now this gray format, gray right pointer, is going to give it to the read clock domain. How we are going to give it? Using the 2DFF. Okay, so what are we going to do over here? So this is my first D flip-flop, and this is my second D flip-flop, and the output of the first D flip-flop is this right pointer gray underscore S1 underscore R, and the output of the second D flip-flop, which is going to give into the read clock domain, is this, which is nothing but right pointer gray underscore S2 underscore R. Initially both will be equal to 0 if reset is equal to 0, and if you have observed, these two D flip-flops are working with R clock, which is read clock domain. Okay, now what is going to happen? This first flip-flop output will be updated to right pointer gray from here, and next flip-flop output will be updated with this right pointer gray underscore S1, and these two D flip-flops are working parallelly. That's the reason I'm going to use a non-blocking assignment. So if I'm going to use non-blocking assignment, then only I can achieve this particular behavior. Now similarly, I should have one more 2D flip-flop synchronizer for sending my gray commit pointer. So I have gray commit pointer which was sending from this particular right clock domain to read clock domain, right? So this can also not be sent directly. You should basically convert this into gray, and you should send it. Okay, so how you're going to send it? So first of all, you should convert it into gray format, and this is the signal which is being converted into gray format. I haven't shown this logic. You can follow the same logic which we have used it for converting binary to gray for my normal right pointer. You can follow that particular logic for converting the normal binary right pointer commit into gray. So this is commit underscore gray underscore S1, and the same logic which we have applied over here. So this is the output which is being given to my read clock domain, commit underscore gray underscore S1. Depending upon this, my read clock domain is going to assert empty from 1 to 0 or not. Using this only, it is going to decide. Okay. Now over here, we are going to basically convert in the read clock domain whatever the gray information we have got, which is right pointer gray underscore S2 underscore R, which we have got from the 2D flip-flop synchronizer, this particular signal. Right underscore pointer underscore gray underscore S2 underscore R, this particular signal which we have got it from the second clock, right? So this we are going to convert it into binary. How to convert it? So I have written a function which is gray to binary underscore r, and I'm passing this particular signal so that I'm going to get my binary information. Just I've written it normally, whatever we do for gray to binary array, that logic only I've written using the XOR gates. And that particular binary pointer is stored in this particular variable, write pointer binary underscore r. And which clock domain it is performing? It is being performed in the read clock domain. So because write pointer is sent from the write clock domain to read clock domain, and read clock domain is going to again convert it into binary form. Now we also need to send one more signal which is known as SAF underscore mode. Okay, so we had an input, right? So which is SAF underscore mode. So my read clock domain also should know, right, what is SAF underscore mode, whether it is store and forward or it is cut through. So I cannot send this signal directly to my read clock domain. I should pass it through the synchronizer. So how I'm going to pass it? Again, I'm using the 2D flip flop synchronizer over here. So SF underscore mode underscore S1 is the first D flip flop output, and second D flip flop output is SF underscore mode underscore S2. And you can see SF underscore mode is being given over here, and I'm going to get SF underscore mode underscore S1 from the first D flip flop, and from the second D flip flop, I'm going to get this SF underscore mode underscore S2. Next, same like we need to pass read pointer to the right clock domain. Again, I'm using the 2D flip-flop synchronizer. You can see the read pointer is being sent to the right clock domain. And this is the signal which we have sent to the right clock domain, which is nothing but read pointer gray underscore h2. Now let us try to understand this particular full condition. So how we are going to calculate the full condition? Right pointer gray, this we already have, and we are comparing with the read pointer gray. This signal where we have got it from, this signal we have got it from the read clock domain via the 2D flip-flop synchronizer. Here we have got it. Using this signal, we are going to convert it with the right pointer, and we are going to calculate the full condition. Now, how to calculate the full condition? Let's say suppose if we have only 3 bits for my write address and read address. That means I have total 8 number of locations, right? So what is it? It is going to look like, so this is my memory, and this is my read pointer, and at the last location, if there is my write pointer. Let's say this is at 000 and this is at 111. So how can I calculate full condition, which is nothing but read pointer is equal to write pointer plus 1. Then I can make this full is equal to 1, because 7 plus 1 is, again you're going to get 0, right? So this is my full condition which I can use when I'm going to have exactly the same number of bits. But over here, if you have carefully observed, and read pointer is of also 4 bits. In this particular case, what are you going to do? So write pointer, if it is at 0, and read pointer, if it is at 0, then your empty is equal to 1. But let's say if write pointer is at the location 8, okay, that is the last location, which is 1000, and read pointer is at 000, then this is nothing but my full is equal to 1. And how we are going to write it down? So for writing this, what we are going to do, we are, and if you have carefully observed, we are basically using this particular write and read pointer in gray format. Now in gray format, what is 1000 value? You can see, which is 1100. So 1100 is my write pointer value, which is represented in gray, and binary read pointer is nothing but 000. You can see, if I want to compare this, what I can do, I can compare the first 2 bits that is being flipped, and last 2 bits are same. Then my full is equal to 1. If the first 2 bits are flipped and last 2 bits are same, that means my full is equal to 1. So that is what I'm writing over here. See, so write pointer gray, if it is equal to complement of the first 2 bits if they are flipped, and read pointer gray, the last 2 bits remain same, then full is equal to 1. That is what we have written over here. Assign full is equal to full underscore enter. That's it. Okay. Now, next is read side logic. So in the read side logic, first of all, we are going to convert whatever the uh, right pointer which was sent, that we are going to convert it into that we are basically converting it from gray to binary. Okay. Then using this particular read pointer, what we are going to do, first of all, we are going to commit underscore binary underscore r. In this signal, we are going to store the right pointer value. So gray to binary, we are going to call this function. And this is commit underscore gray underscore h2. This signal I have shown you, right? In the SAF mode, we are going to get this signal. First of all, we are going to convert it into binary. How we are going to convert it into binary? Simple function I have used it. Okay. And after converting it into binary, what I'm going to do, I'm basically checking for my SAF mode. So effective right pointer, if it is equal to SAF mode underscore S2, this also we have got it from the synchronizer, SAF mode signal there now. Now, if this is equal to 1, whatever the commit signal which is present, that will be equal to my effective right pointer. Now, this will be made to 1 when all the bytes are sent only. Okay, this logic we have already seen. But if a safe mode is equal to 0, then whatever the right pointer value which was sent normally, that will be given to this effective right pointer. That's it. And how I'm going to calculate the empty condition? Read pointer, if it is equal to effective right pointer, then empty will be equal to 1. Now, let's say if SF mode is equal to 1, then this effective right pointer will be equal to 0 until and unless all the bytes have been sent by the processor. That's it. This is what we are going to do. Now, how we are going to calculate almost, so we are going to calculate this almost empty condition by subtracting this. We are going to calculate this almost empty condition by checking this read fill. If it is less than or equal to almost empty threshold. If it is less than or equal to almost threshold, then almost empty will be equal to 1. Now, and coming to this RD data, which we are going to get it from mem underscore out of data width -1. So how we are going to get this mem underscore out? So mem underscore out is a vector which is declared over here, which is nothing but mem of read pointer of address, whatever the address we have, right? So that particular address is being given by this read pointer. So from that locations, we are basically storing it into a vector, and that vector we are directly assigning it to read underscore data. And end of frame, how and end of frame, where are we getting it from? Which is nothing but my MSB bit. Okay. And this is my read pointer advanced logic. So read pointer binary, we are incrementing it, and read pointer after incrementing it, we are going to convert it into gray format. That's it. So this is how we are going to uh, communicate our Mac controller and our processor using this asynchronous FIFO. Yes. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. And if you're having any queries, please let me know in the comment section.